Okay, thank you. So this is just a quick introduction to the matrix library. Basically, because we need a lot of math, and we're trying to decide which matrix library to use, because there are some, like Dan mentioned, Boost, and there's Eigen, there's a couple of others, the JAMA and stuff. But most of these libraries, they're trying to be kind of like as much similar to MATLAB, or very trying to play like high level library. So we wanted a really simple low level library that we wanted to avoid all operators. We wanted to avoid all automatic resizing, all automatic initialization and stuff like that. I don't know whether it's So that's why we decided to build a matrix library that would be somehow based on the BLAS routines, because they're fast. We used them in our previous project. So as I said, the library calls the Atlas or BLAS functions for the high level math operations like inversions or Kaldi decomposition and stuff. We use the LAPAC, one of those implementations. And for the code, okay, we also use this Atlas, this highly automatically tuned linear algebra system. I don't know, which misses some of the LAPAC implementation. So we use public domain code from the JAMA project to implement some of that stuff. So here's just a quick example. So it's templated. It's templated on doubles and floats in C++. Basically, the basic classes are here. So we have the matrix, the standard matrix rectangular library. Then we have the vector. Then we have something SP and TP matrices. So this is something that Dan mentioned before. So SP is a symmetric packed matrix. So basically, what you do is that if you know that your matrix is going to be symmetric, you can just store the lower triangle. The lower triangle of the matrix and put the coefficients one after another and pack that matrix in memory. And but SP just tells you that you know that this is going to be symmetrical. The same as TP, which is just like triangular packed matrix. You just know that it's you have to treat it as a triangular matrix with the whatever is above the diagonal of the matrix is set to 0. The nice thing is that LAPAC really supports and BLAS they support these two kind of matrices, and the code is optimized somehow. This is just a quick example. So the only operators that we use are for indexing the structures. So you see that we can create a vector of floats with the fixed size. Then you can iterate over the elements. You can access them, as I said, with the we don't use square brackets. We use normal brackets like here. We don't use operators because they're just difficult to debug, and I mean we want it to be as much C or C++ as possible. So everything is called by functions. So you see here you can add a vector and that's basically it. So there's no auto resizing or anything like that, because normally you have to know what you're doing. So if there's something wrong, then no iterators. That's too difficult, and maybe but
well, you can get the pointers directly.
You can get the pointers directly. Yeah, you can get the pointer to the row. You can get the pointer to the beginning of the memory space. Or this is the next example. So just to show you the format of the function. So you've got usually the functions take some trans and no trans parameters, so that you know if you want the matrix that you put in as a parameter, if you want to transpose it or not. Most of these functions are really based on the BLAS gem functions, because that's really one of the most used functions. So this is the format of the gem function. So usually you have a matrix and you want to add some multiplication of two other matrices to it while weighting it with the matrix itself. So this is something that we use a lot. some notes about the namings. I guess that's all documented in the Doxygen that is on the SourceForge. Yeah, if you wanna multiply two or make some operation on two same identities, you would use the two there. So this is just a naming scheme. Yet another example from the high level math. So you see that you can create a normal matrix. You can create a symmetrical packed matrix. Uh, you can create some. Yeah, sorry, say it again.
With the symmetric product of the
Yeah, yeah, the symmetric dot product here. So you see that you really have a special function. So scatter, sorry, the matrix scatter really knows that it is a symmetrical packed product. So it does this thing effectively and stores it effectively. Another thing is you can create a triangle packed format, which is good for the Kaldi stuff. So you just take that symmetric packed matrix here. This function already knows that it's it's symmetric packed, so it stores it in an efficient way again, and it inverts, and it's gonna be does what it does. Yeah. So yeah. Another thing that is supported is like submatrices. So it's basically just derived from the matrix or vector or whatever there is. So these classes they you can do exactly the same stuff as with the original matrix class or vector class, except they don't accept any resizing or reshaping or anything like that. Only they let you do only the non resizing, and basically you're just addressing the space that was already pre-allocated by the matrix. So there's nothing like automatic deallocation or something. Yeah, this is an example. So if you wanna address a subvector of your 10-dimensional vector, starting at a second element and having 10 elements in it, so you can do it like this. Here's how you do here's how you index a matrix starting at the first row, having 10 rows. 10 rows in total, starting at the first column. Well, this is the second column indexing. This is C-style indexing, and yeah, here you can just use it as you would with the standard matrix class. So it's not memory safe, but that's something that the C programmers usually do know. Like it's nothing that you don't want to prototype your code somehow. Once you start writing in C, you have to be careful about memory. So I guess this is something quite natural to the C language. And also there's no representation of matrix columns. Like I think we'll work on that maybe later or something. Yeah, so you already saw the functionality in the example. So we have matrix inversion, Kaldi decomposition, SVD, eigenvalue, fast Fourier transform, and the nice thing is that there's an extensive code included in the package. So whatever we do, we always know that if we change the code, we know that it works. Yeah, that's it. Do we support sparse? No, we don't. That's what Dan already mentioned in the first part of the talk. Because this speech stuff is not. We don't use sparse matrices that much. No. In the
If you want to add it, then
if you want to edit, yeah, you're welcome. Yeah, please.
I know you guys are trying to put sparsity into speech, but
What about assets?
That's something that is because this library. Actually, the nice thing about this library, which I didn't mention, is somehow independent. It only includes the base class of the Kaldi. So if you don't want to use the rest of the Kaldi, you can just use this thing, and it calls some error stuff. I don't. Dan, maybe you can comment on that. That's in the base. That's in the base. So
when I say base, I mean the base directory. There's a small directory that contains the stuff that this depends
that is
on.
common to all like basic data types and stuff like that.
The point is that we've kept to a very minimum the amount of dependencies that this has on other Kaldi stuff, so you don't have to compile all of Kaldi. done by exception.
It's just like some I/O and some error handling. That's what it depends on, because these objects can be read or written.
So I think we.
And maybe just to mention that there are some input output, that the only operators are really the brackets and input output, you know, the C++ IO stream style. Yeah.
So we're going to have a short break and again allow people to escape before I go through some of the scripts. So maybe after about 3 to 5 minutes we'll start again.